Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on analytical dynamics or classical mechanics, chapter Lagrangian dynamics, lecture number 5, in which I will derive Lagrange's equations of motion in other cases. Now, we deal the case 2, in which we will find the Lagrange's equations of motion of second kind in the case for non-conservative system or non-natural system. Let generalized component of external applied force Qi can be expressed in the form Qi equal to d by dt partial derivative of u with respect to Qi dot minus partial derivative of u with respect to Qi, I equal to 1, 2, n, where u is a function of generalized coordinate Qi and generalized velocity Qi dot. That is, u is the function of Qi and Qi dot. This is number 2. Since Lagrange's equations of motion of second kind be d by dt partial derivative of t with respect to Qi dot minus partial derivative of t with respect to Qi equal to capital Qi, I equal to 1, 2, 3 n. This is equation 3. Using 1, this concept, in 3, in this place we write right side of 1. We get this equation. Here we take the terms in left hand side and we will get d by dt partial derivative with respect to Qi dot. Here we have t, here we have u, that is t minus u, minus partial derivative with respect to Qi, here t, here minus u, here minus, so this is minus u. This t minus u is L, so we write in this place L and we get equation 4. Here L, t minus u equal to L, which is called Lagrangian function or kinetic potential for a non-conservative system. The function u, this u, is regarded as generalized potential energy function for non-conservative or non-natural dynamical system. Although this force is not conservative force, but in place of conservative force we have applied this force. This is Qi for non-conservative system or non-natural system. So we call this as generalized potential energy function. Now case 3. Here we find the Lagrange's equations of motion of second kind when the system is partly conservative and partly non-conservative. Let the dynamical system be acted upon by the forces F mu vector along with non-conservative forces F mu prime vector. The virtual work done by non-conservative forces F mu prime for virtual displacement delta r mu is given by delta W work done is force multiply displacement. This is dot product. We may write delta R mu vector as sigma I equal to 1 to n partial derivative of R mu with respect to Qi delta Qi. We take this sigma outside and under bracket we write sigma mu f mu prime vector dot partial derivative of R mu vector with respect to Qi and here delta Qi. This is number 1. This delta Qi is the generalized virtual displacement and left side is work done. So this part will be generalized component of force. Therefore the coefficients of delta Qi are known as components of forces corresponding to generalized coordinates Qi and are denoted by capital Qi prime. Capital Qi prime is this under bracket sigma mu f mu prime vector dot partial derivative of R mu with respect to Qi. This is number 2. Let Qi be the generalized component of forces for conservative system. This Qi prime is for non-conservative system and this Qi is for conservative system, generalized component of forces. Then Qi is written as minus partial derivative of V with respect to Qi. V be the potential function. Negative of derivative of potential function is the force. This is number 3. Therefore, Lagrange's equation of motion for the system when the system is partly conservative and partly non-conservative, we may write this d by dt under bracket partial derivative of t with respect to Qi dot minus partial derivative of t with respect to Qi. Right side Qi, capital Qi plus capital Qi prime. This capital Qi be the corresponding to conservative system and Qi prime be the quantity corresponding to non-conservative system. Here this is for I equal to 1, 2 dot 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 n. We put the value of Qi taking from 3 here. This is minus partial derivative of V with respect to Qi. This is number 4. Implies that this term remains same, this term remains same. We take this term minus partial derivative of V with respect to Qi left side and in right side Qi prime left. Here we write d by dt partial derivative with respect to Qi dot here t minus v, because here it was only t, here we have written t minus v because partial derivative of v with respect to Qi dot is 0 here, because potential function is the function of position coordinates, not velocity. So it is independent from velocity. So derivative of v with respect to velocity Qi dot is 0. So here if we include v, there will be no hull. Here we take minus, here partial derivative with respect to Qi, here we take t minus v and right side be same Qi prime. Since t minus v equal to L Here we have written L, where T minus V equal to L. So here we have written L, here we have written L, and here Qi prime. This is the required result. Now, case 4. We shall find the Lagrange equations of second kind for non-holonomic system. Since the equations of virtual work may be written in the form the sigma I equal to 1 to n under bracket d by dt partial derivative of t with respect to qi dot minus partial derivative of t with respect to qi minus qi bracket close delta qi equal to 0. We have already calculated this earlier. This is number 1. We know that in the derivation of Lagrange's equations for a holonomic system requires that the generalized coordinates be independent. That is, generalized virtual displacements delta qi's are independent. But for non-holonomic system, this principle is not applicable. That is, all delta qi's are not independent. They satisfy M equations of type this. Sigma I equal to 1 to n a j I delta qi equal to 0. J equal to 1, 2, dot m. So we get M equations of this type. This is number 2. Lagrange's method is to multiply these equations by lambda j. J equal to 1, 2, dot m, and then add to the virtual work equation 1. So here we have written up to this qi, and then we have added sigma j equal to 1 to m lambda j a j I delta qi. This equal to 0. The technique to solve this equation is that we shall assume that the first m coordinates are dependent and later n minus m coordinates will be independent. If first m are dependent, then we choose the arbitrary lambdas, this, in such a way that coefficients of first m number of delta qi's vanish. We choose this lambda j, m number of lambda j's, then they will vanish, and then the coefficients will vanish by virtue of dependent character, and then other coefficients will vanish due to by virtue of independence of letter n minus m number of delta qi's. Thus, n equations may be written as d by dt partial derivative of t with respect to qi dot minus partial derivative of t with respect to qi minus qi plus sigma j equal to 1 to m lambda j a j I equal to 0. I equal to 1, 2, 3 dot n. If the forces are derivable from potential function, then we know that qi will be equal to minus negative of partial derivative of v with respect to generalized coordinate qi. We put this result in this equation here, then we get here partial derivative of V with respect to Qi. Here minus, plus. Now, we write here, in place of t, we may write t minus v as partial derivative of v with respect to Qi dot is 0, because v be the potential function and potential function is the function of position coordinates only, not velocity. So with respect to velocity, this partial derivative will be 0. So if we write here minus v, there will be no harm. Here we take minus common, here t, here v, and other terms remain same. Here we write in place of t minus v as L, and we get this equation. This is the standard form of Lagrange's equations of motion for a non-holonomic system. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.